So, welcome back to lectures on engineering mathematics 2. So, this is module number 4 on Fourier series and integral transforms, lecture number 31, and today we will discuss on trigonometric polynomials and trigonometric series. So, just first let me tell you what we will be covering in this module 4. So, it is Fourier series on and this integral transforms. So, there will be naturally two different sections. So, one will be on Fourier series and the other one on integral transform. So, Fourier series mainly we will see there it is used in a nutshell to approximate the functions using sine and cosine functions, which are simple and then also periodic. So, and the second portion the other applications. So, we will be also talking about some applications. So, the Fourier series has several applications, including this analysis of this current flow, sound waves, in image analysis, and solution of many differential equations, including partial differential equations, etc. The second portion will be on integral transform, and we will also observe there is a connection from this Fourier series to the integral transform, in particular the Fourier transform. So, that will be also studied, and we will be talking about in general two types of integral transform. One will be on Fourier transform. So, that is exactly related to the Fourier series, and we will see the transformation from the Fourier series to the integral transform. There will be one more integral transform, the Laplace transform will be discussing in this lecture, in this module. And concerning this integral transform, so we can explain in this way basically the motivation behind this integral transform. So, we will be covering this portion, that the initial and boundary value problem when we try to solve directly. So, this getting the solution is very difficult for the in these initial value and the boundary value problems. So, they are the differential equations associated with some kind of conditions to have unique solutions. So, those portion we will be covering in those particular lectures. So, what we do usually, we apply the integral transform to the initial value and the boundary value problem, which is normally easy, and it converts the problem to a simple problem, either algebraic problem or we are talking about the partial differential equations there. Then this integral transform will convert to the ordinary differential equations, and in either case both of them are easy to solve, and then we apply the integral transform to get the solution again. So, this is a kind of technique which will be demonstrated in our lectures to get the solution of the differential equations using these integral transform, and directly if we try to get those solutions, they will be very difficult, but with the help of the integral transforms they will become very easy. So, we will start with the Fourier series. There will be about 10 lectures on Fourier series, and followed by the 10 lectures on Fourier transform, and then about 10 lectures again on Laplace transform. So, in this today's lecture we will be discussing what are the periodic functions, because there is a connection of the Fourier series to periodic functions. So, we will start with what are the periodic functions, and then this is a very basic introduction to get prepared for discussing the Fourier series or to construct the Fourier series in the next lecture. So, we will be talking about the trigonometric polynomials and trigonometric series, and further as a whole we will be also using this term trigonometric system in today's lecture. So, let me start with this periodic functions. So, if a function f is periodic with period this t, then the f t, the function value at t, must be equal to the function value at t plus this capital T, and then we call that this t is the period of the function, and the function is periodic if this property holds for all t. And the smallest value of t, this capital T, which we are calling period, for which this equality holds, because once, I mean, we will observe also later that once we find some this capital T such that this property holds here, then the 2t or the 3t, any integer multiple of this t will also work and this property will be true. So, if f t is equal to f t plus this capital T, then also f t is equal to f t plus 2 times capital T or 2 times 3t, etc. So, the smallest value for which this equality is true is called the fundamental period of the function f t. So, if this t is the period of the function f, then n t, which I have just discussed for any n natural number, is also a period of t, and as a whole we are talking about the smallest of such t for which this equality is true, and this is called the fundamental period of t. So, there are some interesting properties of the periodic function, some of them I will list here. So, the first one, that the sum, difference, product or quotient of two functions is also periodic. So, if we have two functions, their sum will be also periodic, their product will be also periodic, their difference will be also periodic, their quotient will be also periodic. That is a nice property we have for this periodic function. So, for instance, if we take this f x is equal to sin x plus sin 2 x plus sin 3 x. So, we have added three periodic functions. So, it is well known that the sin x is a periodic function, or sin 2 x or sin 3 x. All these are periodic functions with different period, different fundamental period. So, what is the period here for this function, which is sum of the three different periodic functions? So, the period we will look individually first. So, what is the period of this first function, that is 2 pi, it is known, and for 2 x, when we are talking about sin 2 x, the period will be half, because we are talking about 2 x there. So, usually we compute 2 pi and divided by this number will give the period of this sine or cosine functions. So, here we have the period pi, and similarly for the sin 3 x we have 2 pi over this number 3 here. So, here the period is 2 pi by 3. So, 2 pi period, and then 2 pi by 3 period. So, to get the period of the sum, what we have to do? We have to just find the common period of all these functions. So, here for example, sin 2 x has 2 pi period, then the sin 2 x has pi period, but we also in the previous slide we have already discussed that if pi is the period. So, if it is repeating its value after pi, definitely it will also repeat its value after 2 pi. So, and as a result we are calling that if pi is the period, then n pi is also a period. So, here the 2 pi is also period for this function, and for this function if I multiply by 3. So, again the 2 pi is also period of that function. So, the common period of all these three functions, what we observe is actually 2 pi, and as a result we can tell something about the period of this f x, because this is repeating its value after 2 pi period, this is repeating after pi, and naturally after 2 pi also, and this is also repeating after 2 pi. So, the sum will also, as the sum function will also repeat its value after this 2 pi period, which is the common period of all these functions sin x, sin 2 x and cos 3 x. So, it is a 2 pi here. We can observe, we can clearly see that f x plus 2 pi is equal to sin x plus 2 pi, sin 2 x plus 2 pi and cos 3 x plus 2 pi. We have added this for x, we have listed here x plus 2 pi. So, what will happen? So, here f x is replaced by x plus 2 pi, here also x plus 2 pi. So, this will become as 4 pi, this will become as 6 pi, whatever. So, here this sin x plus 2 pi is sin x, here also sin x plus this 4 pi is also sin x, and this is also cos x, because all these functions have the period pi, 2 pi or 2 pi by 3. So, this is sin x, sin 2 x, cos 3 x, again the same function f x, and therefore, this is a periodic function with period 2 pi, because f x plus 2 pi we are getting this f x, and this is indeed the fundamental period, because the common period is 2 pi and not less than 2 pi. So, that is going to be also the fundamental period. So, another interesting property which we will discuss here. So, if a function is integrable on any interval of length t, then it is integrable on any other interval of the same length, and the value, the interesting part is that the value of the integral is same over, as long as the length of the interval is same, and we are talking about the periodic function as its integrand, then the value of all the integrals will be equal. Only we have to see that the length of the interval where we are integrating this. So, then the value of the integral is going to be same. So, let me just elaborate more. So, here if f x is periodic with period t, then if we integrate this a to a plus t, the value will be same if we integrate from other point b to b plus t, b plus t. So, here the length is t, here also the length of this interval is t, and that value will be same if we integrate from 0 to capital T. So, in the whole this period t. So, all these values will be same as long as we have we are covering the whole period capital T. This can be visualized from this figure. So, if we are suppose this is a periodic function here, from here to this, and then we have this here, and then again this starts from here and so on. So, it is a periodic function. So, from here to here, that period ends, this point to this point, that is the period. So, if we integrate this a to a plus t. So, what is interesting here, if we started at this point a and then covering this period t. So, whatever portion was left here, we have covered actually here, and this a plus this t. So, the area under this curve f x is going to be the area of these two rectangles. So, one this one and the other one is this one. So, and either we start from other point this b, the same situation, whatever we have left here, for instance it is covered here. So, ultimately in any case, whether we are integrating from a to a plus t or b to b plus t, the area of these two rectangles, the smaller one and this bigger one, is covered, which is same as if we integrate from 0 to, for instance, this t, again the area of these two rectangles will be covered. So, that is the interesting property, that whenever we have this periodic function, we can integrate from any point to that point plus the period t, b to b plus t, or from 0 to 0 plus t. So, from any point we can start and then cover the whole period, and that will be all those integrals will be equal. Okay, so, what are the trigonometric polynomials and then trigonometric series we will be considering now. So, the trigonometric polynomial of order n is defined as this some constant and then sum of the cosine and the sine functions with again some coefficients here sitting in front of cos and sine. So, and since there are n such terms are added for having this cos and sine terms. So, we call this trigonometric polynomial of order n, and the period of this polynomial which we are denoting as n x will be the common period again of all these sine and cosine, because here what we are doing, we are adding the cosine, sine, cosine, sine functions, and the common period if we want to see for this finite sum, in this case will be the common period of all these functions which are being added here to construct this such a so called the trigonometric polynomial. So, the first here when the k is 1, it is a cos pi x over L and sin pi x over L, then we have cos 2 pi x over L, sin 2 pi x over L, and so on. This is continued until we got this sin n pi x over L and cos n pi x over L. So, if you want to get the common period of this, remember from the previous simple example, the common period was coming with this the first function itself, because here we have 2 times here, then 3 times n times. So, the period of those functions will be smaller, the largest will be from the coming from the first function, and others are just the multiple the other periods we can multiply by natural number to get this period. So, that is going to be the common period. So, common period will be 2 pi, and then we have to divide by this pi by L number, this number pi by L. So, the 2 L. So, for this trigonometric polynomial, which is just the addition of all these functions whose common period is 2 L. So, the period for this S n x for this function here or for this polynomial will be 2 times L, and the trigonometric series we call the infinite. So, infinite trigonometric series, when the k goes from 1 to infinity. So, instead of this n, if we are going for infinitely many terms, we call this infinite trigonometric series, and in this case, if this series converges, I mean this is another interesting point, that if this series converges, because now we are talking about infinite series and the series may not converge, but if this converges, in that case if it converges, this also represents a function of period 2 L, because for this when n is finite, we have seen that the period of this 2 n or S n x is 2 L. And now, here we are keep on adding these terms, but that common period will not change, that will remain 2 L itself. So, if this series converges, then that function to whom this is converging, that will be a 2 L periodic function. So, that is another information which we need here for explaining the Fourier series in the next lecture indeed. So, here we have now introduced in this trigonometric series or the infinite trigonometric series and the trigonometric polynomial in terms of the cosine and sine functions. So, just a remark. So, though the sine and the cosine functions are just very simple functions and we know the graph of each of them, but what is interesting that their sum may be quite complex, and I just want to clear this point, because later on we will see that many complicated functions can be represented in terms of the sine and cosine functions. Just a simple example if we take, which we have just seen before, sine x sine 2 x and cos 3 x, for instance, if we take this function whose period is going to be 2 pi, the common period of all these functions here is 2 pi. So, the period of this function, the sum function is 2 pi. So, if we just plot this, what will happen? We can see this is not as simple as we perhaps expected from the sine and the cosine functions. So, here for instance, if we say this starts from 0, then it is having this curvature here and then goes up to this 2 pi, and then again this repeats its value. So, this is in one period, the function starts from here and continue up to this point, and then it repeats its value. So, from here to this point, it is a one period, covering one period, that is a 2 pi. So, at this point here we are somewhere at 2 pi, and then it will repeat its value. So, this sum of these just three simple functions represents this complicated behavior then we can imagine that we have if we have a possibility of having many more terms or infinitely many terms, that too with some coefficients here sitting with this cos and sine. So, we have a full flexibility of getting a desired function in terms of the sine and the cosine functions, and that is what we will exactly do in the Fourier series. In the next lecture we will observe that. Okay, so, the function has this period 2 pi, which is a common period of all these three functions, which I have already discussed. And a very interesting property now we will look into for trigonometric systems. So, what is the trigonometric system? We are calling the sine, cosine and so on, sine 2 x, cos 3 x, that is a system with having cosine and sine functions, and that is called trigonometric system. So, we call that two functions phi x and psi x to be orthogonal on this interval a b if we integrate from a to b the product of these two functions, and if it is 0. If the product of the two functions integrated over the certain interval here a b is 0, then we call that these two functions are orthogonal in this interval a b or on the interval a b if this integral is 0. So, now we have the result for our trigonometric system. So, the basic trigonometric system we call the basic trigonometric system when we have the simple functions 1 cos x, sin x, we have cos 2 x, sin 2 x, etc., and this can continue to whatever number we want. So, this basic trigonometric function is what is interesting here, and we will prove this fact that this is orthogonal on this interval minus pi to pi, or we can take any other interval, for instance 0 to 2 pi or a to a plus 2 pi, as long as we are covering the length this 2 pi, then for because this is the common period for this is 2 pi for this system here. So, this is orthogonal on the interval minus pi to pi or 0 to 2 pi or any number a we can take, and a plus 2 pi, this is also fine. So, this is we will observe that this basic trigonometric system, this is orthogonal. What do we mean? If we take any two functions from this system, for instance we take one, we take cos 2 x and 1 into cos 2 x and then integrate from this minus pi to pi dx, this must be 0. This is clearly visible here too, but we will formally prove in the next slide. So, if we take any two members of this family, any two members from this system, and their product when integrated over this interval minus pi to pi, the value of this integral is going to be 0. This is what we will observe now. So, we will consider different cases. First, we are considering here that if n is not equal to 0, it is an integer we are talking about, but which is not equal to 0. And then we have the following integrals to show the orthogonality of the function 1 with any other member of the sine or cosine family. So, as at first what we are looking for, so 1 is also a member of this trigonometric system. So, this 1, and we will take with any other sine or cosine function, either sin x, sin 2 x, cos 2 x, etc., and we will show here that these two are orthogonal, one with any other trigonometric any other member of this trigonometric system from the sine or cosine family. So, here if we take 1 and for instance is cos n x, n could be anything other than 0, because if n is 0, this is going to be 1. So, which that the same member we will be making the product. So, that we are avoiding here the two different members. So, this is one member and this is the another member of this trigonometric system, and if we integrate from minus pi to pi. So, it is just the product is cos n x. So, the integral will be sin n x over n and then minus pi to pi. Sin n pi is 0, sin minus n pi is also 0. So, the result of this is 0. So, here we have seen that with 1, if we take any member of the cosine family, that means the cos x, cos 2 x, cos 3 x, cos 5 x, etc., these two are orthogonal. Similarly, we can also prove that with 1, if we take any other member of this sine family from our trigonometric system, then again we can see that this is cos n x over n, and here, or indeed from here directly we can say sin n x is a odd function and the value is 0. So, the value of this integral is also 0. So, this at least we have seen that with 1 we can take any member of the cosine family or any member of the sine family, and these are orthogonal. We can also check this following useful results, that if we take the same member, that means the cos n x, meaning cos x or cos 2 x with cos 2 x. So, they are not different members. So, they are the same members. What we have said in the earlier result, that the system is orthogonal, that means any two different members if we take, they are orthogonal, but not the same member. So, here we are taking the same member, we have taken the cos n x and with cos n x for same n of course. So, if we have taken the same member, in that case this is not 0, and we will observe now that what is the value coming. So, this cos square n x we can convert into this 2 angle, the double angle 2 n x. So, 1 plus cos 2 n x by 2 with the trigonometric identity, we have this result, and then this value is coming to be pi. How pi? So, the first integral is this half is integral minus pi to pi and the dx. So, here is dx missing dx. So, and the second one, so the plus again half, we have minus pi to pi and we have cos 2 n x and dx. So, this cos 2 n x dx we have just seen above that this is going to be 0 with any number n x there. So, this integral is 0, whereas the first one gives half and this is 2 pi. So, we get the phi as a value pi there. So, here we have the value pi. So, cos square n x dx is equal to this one and is equal to pi. So, when we take the same member of the family, then the value is pi. Similarly, if we take the sine from the sine family, the same member sin n x, in this case also we can observe that this is 1 minus cos n x by 2, and again the second integral will lead to 0, and this half and integral minus pi to pi will give us pi. So, here the value is pi in either case. The only member left is 1. If we take 1 with 1 and then integrate from minus pi to pi dx, in this case the value will be 2 pi naturally. So, these three situations we have covered. One, when we have taken the same member from the cos family, value is pi. The same member from the sine family, again the value is pi, and the same member of this 1 itself, because 1 is also a member of the trigonometric system. In that case, this is 2 pi, and 1 with any other member of the cos is 0, 1 with any other member of the sine, it is 0, and there is now something left here to be proved, that any two members we can take of the different two members of the family, it is a 0. So, here we have only proved that with the 1, if we take any other member from the system, it is 0. So, now we will continue this proof. So, we will take now for any integer m and n, when these two are not equal, that means first for the cosine family we will take. So, cos n x and cos m x. So, when m and n are equal, we have seen the value is pi. So, but now we have two different members, one is cos n x, another one is cos m x. When n and m are not equal, so they are different member of the family. So, in this case we again use the trigonometric identity 2 cos a cos b. So, with half here. So, cos this n x plus m y and then n x minus m y, and the integral is from minus pi to pi. So, here the sign will come when we integrate, here also sign will come, and then with pi and minus pi, in either case the value is going to be 0. So, again when we take the two different member of the cosine family, the value is 0. Similarly, if we take from the sine family also, the same situation will happen. So, again this trigonometric identity will lead to the cos only with the negative sign there, and when we integrate this, again sin n minus m sin n plus m will come, and x, and when we have to substitute the value pi and minus pi. So, sin integer times pi is 0 and sin any integer times pi is 0. So, this will also lead to 0. So, we have also seen that if we take two different members from the same family, it is going to be 0. If we take fix one as a member and take any other member from the cosine or from the sine, that is 0. So, what is left now, that for any m n, if we take one member from sine family, other member from the cosine family, then what will happen? So, for any integer m n n, we will show now that any two members of the two different family, means sine and cosine, they are also orthogonal. So, we take sin n x and then the cos m x, the two here, the two members, two different members. So, one from sine, one another from cosine. So, here n and n may be the same, because the family is different, one is coming from sine, another one is coming from cosine. So, we can talk about sin x cos x. So, that value will be also 0, and here the reasoning is very clear. The cos is the even function, here sine is the odd function, and when we integrate minus pi to pi, this integrand is odd. So, the value is 0 irrespective of whatever n or m is. So, the theorem, what is, we have a more general result than what we have just proved, where we have taken the basic, the fundamental trigonometric system where the period was 2 pi, but for a rather general trigonometric system where the period is not 2 pi, but it is 2 L, we can also prove the same similar result, that this trigonometric system, and now we have generalized the system. So, we have taken 1 and cos pi x over L, sin pi x over L, cos 2 pi x over L, sin 2 pi x over L, and then we will continue with cos 3 pi x over L, sin 3 pi x over L, etc. So, here this trigonometric system, the period is 2 L now instead of 2 pi. So, in this case, this is orthogonal on the interval minus L to L. If we go from minus L to L, we are covering the period 2 L, or A to A plus 2 L we can go, where A is any real number. So, this trigonometric system is also orthogonal in these intervals minus L to L or A to A plus 2 L. So, this is a more general result than the earlier one which we have proved. So, this we are not proving, but exactly the proof follows the similar argument what we have just done there. So, the common period of this trigonometric system is 2 L. This can be easily obtained from the period of this first two functions, which is 2 L. So, and what result we have now? It is if minus L to L we integrate the cos m x and the cos n x. So, for different m and n, then the value will be 0, and if we have same m and n, then the value will be L. Earlier it was pi. So, if m is not equal to n, the value is 0. So, they are orthogonal if they are two different members, but if they are the same member, then the value is L. This is the result can be proved. Or minus L to L sine, for the same sine family also we have the same result, that it is 0 when there are two different members of the family, and if they are the same, then the value is coming as L. And we can we know already for periodic function, whether you integrate from minus L to L or from A to A plus 2 L, the value will be the same. Another result, that we can have two different members now, sine and cosine, one from sine family, another from cosine family, and then we will observe that this is also 0. So, this is a very important result which will be used in the next lecture. So, what we have now, that is a remark. So, for L is equal to pi, this system reduces to, so if we put L is equal to pi, so it is simply that system which we have discussed before, 1 cos x, sin 2 x, etc. So, this is the same system, the standard trigonometric system of period 2 pi, this one which can be just obtained from this one, and the value of the integral. So, which was the earlier result which we have just discussed, the over the length of the period of integrand is equal to 0 if the integrand is a product of two different members of the trigonometric system, and if the product is from the same member from the sine or the cosine family. So, we are taking about sin x or sin 2 x. In that case, it is the value is the half of the interval length. So, if we are talking about minus L to L, so the value will be L, or we are talking about minus pi to pi, the value will be pi. This is what we have seen. So, these are the references which we have used for preparing this lecture. And just to conclude, so we have basically discussed the trigonometric polynomial today, which is this finite sum of the cos and the sine function, and we have also discussed the trigonometric system, which is 1 cos pi x sin pi x over L and so on. And the interesting property of this trigonometric system, which we have also proved, it's that this system is orthogonal on this interval minus L to L. That means, any two members we take and the product, if we integrate over minus L to L, the value will be 0. So, we can take any two different members here, and the product, if integrated over from minus L to L, the value will be 0. So, that is all for this lecture, and I thank you for your attention.